So we'll continue our discussion on optimization, dynamic optimization. So in the previous lecture, this was the problem. I have the state update equation. I want to minimize J of U. So I'm using x equals to x0 to xt plus 1, u equals to u0 to ut. So I want to minimize over all u, ju, which is ct plus 1 xt plus 1 plus summation ct xt ut. T goes from 0 to capital T. So this is called the performance index. J is called the performance index. It's a function of the entire trajectory of u that you are taking, and it's a running cost and a terminal cost. And what we wanted to prove, or what we did in the previous class, we wanted to find the gradient of J with respect to U, because we wanted to get the necessary conditions for optimality. So the necessary condition for optimality is that if I'm trying to minimize U in Rm cross T, so if I want to minimize U over this particular space, the first derivative has to be equal to 0. That's what we learned from the first order necessary condition for optimality. And then we did a lot of mumbo jumbo, and we figured out that if we define p t plus 1, sorry, p capital T plus 1 is gradient xt plus 1 ct plus 1 xt plus 1. So this x is the variable, this x is the point, the terminal state, and then I define pt recursively as, well, let me define ht of xt ut pt plus 1 equals to pt plus 1 transpose ft plus ct. Well, let me just write it completely. And let's say U star is the optimal solution. So the theorem we covered in the last, it's just a small part of Pontryagin minimum principle. So we are not doing the general version of Pontryagin minimum principle because that's a more complicated theory. So what we are doing is a very simple version of Pontryagin minimum principle. So U star is optimal solution, optimal action, X star corresponding trajectory. So whenever we say trajectory, what we are talking about is a sequence of states that are visited under the influence of the specific action. So in this case, we are picking the optimal actions. We're looking at the corresponding trajectory that is generated, and then what we had proved in the previous lecture is gradient of ut of j u is equal to gradient of ut of ht evaluated at xt ut pt plus 1. And what we had said, so this is the first thing we had discussed in the previous class. And the second thing is, at the optimal solution, this has to be equal to 0. So at ut star, or at u star, so this part where pt plus 1 star equals to gradient of xt of ht evaluated at xt star, sorry, pt star, pt plus 1 star. Okay. And p capital T plus 1 star is gradient xt plus 1 ct plus 1 evaluated at xt plus 1 star. So this is what we did in the previous lecture. These are the results that we proved in the previous lecture. I mean, you have written it down already in the previous lecture, so, but I'm still waiting because I see some of you writing. So I'll just wait. Okay, so this is the co-state vector. Co-state vector runs in a backward fashion. So if u star is the optimal action and x star is the corresponding trajectory, then the derivative of the Hamiltonian with respect to ut will be equal to 0 along the optimal trajectory, where pt plus 1 star, the co-state vectors are defined recursively in a backward recursive fashion. So you take the derivative of the cost function with respect to xt plus 1 star, and then you define pt plus pt star as the derivative of the Hamiltonian with respect to xt, again along the optimal trajectory. And given that this is what the gradient of j at u looks like, the way to solve the problem at every point of time is the algorithm called backpropagation algorithm. This algorithm is also used to train neural network. So you get, so initialize u0. So this is not the u at time 0, this is the entire trajectory of u for iteration k equals to 0. And then you compute x0 using xt plus 1 equals to ft xt ut. This is known as a forward propagation. Then you compute p0 using pt plus 1, pt equals to gradient t, gradient xt of ht. This is known as backward propagation. And then set u1 equals to u0 minus alpha 0 gradient u. of Ju, or alternatively ut1 equals to ut0 minus alpha 0 gradient of ut of ht. And once you do this, then you go back to this step. And this entire algorithm is known as backpropagation algorithm. So once you get the new set of actions, you recompute the forward trajectory, then you do the backward propagation in order to compute the co-state vectors, and then you update your actions using the forward propagation and the backward propagation values. Okay. If you want to use the second derivative, if you wanted to use the Newton's method, then there'll be a second derivative inverse here. And that expression is a bit complicated, so we won't cover it in the class. But it's there in the book. So those of you who want to know how to do Newton's method for this case, you can look into the book and find the algorithm for the case of second order method for backpropagation. So how do we use it in the neural network? So in the neural network, xt is the output of each layer, ut are the weights. So those of you who are not familiar with neural network, you don't have to remember this. But those of you who are, I just want to make the connection. I think there is a question in the assignment, and so through the assignment you will have much better clarity of how this is used in neural network. But xt is the output of every layer, ut are the weights. We are trying to optimize the weights, and you only have a terminal cost there. You don't have a running cost. We don't care about what the weights values are, as long as at the terminal time the output is the desired output of the neural network. And so you essentially train the weights u by using this backpropagation algorithm, an instance of this backpropagation algorithm. Okay, so this algorithm was designed. I mean, of course, this idea was known back in 1949, 48/49, because Pontryagin was a professor in USSR, and he was working on this, and he came up with the first result, which was in public domain at that time, and that was in the continuous time, so it was a bit more complicated setting, and Pontryagin was a mathematician, so the paper was written in a mathematics journal and so on. But within the learning community, this kind of algorithm was developed several times. Like, it was rediscovered several times in 1950s and 60s and 70s. But at least sitting in 2025, we can look back and we can argue that all of them were instantiation of the same algorithm. So whatever other people did in their papers, it was all instantiation of the same algorithm that was designed back in 1949 or 48. This algorithm, I mean, like I said, this dynamic optimization, the reason why dynamic optimization was being studied, the reason why static optimization was being studied was because of World War II. The reason why dynamic optimization was being studied was because of Cold War, because you wanted to send missiles on each other's land and you wanted to send satellites in the space. And that was part of the Cold War, right? Sending satellites to space was part of the Cold War. So yeah, a lot of this development happened because each country wanted to win the space race or win the war. Okay. Now I want to, any questions on the backpropagation algorithm? Would you be able to run backpropagation algorithm on your own now that you know the theory? Right. So if you are, nowadays you apply these algorithms on what? On vehicles, hybrid vehicles, electric vehicles, air conditioning optimization, what else? Energy optimization. SpaceX is sending rockets into the space and getting it back. So those kind of problems. You also have robotics, humanoid robotics. So nowadays, I don't know how many of you have seen, but there are like Boston Dynamics has a dog called Quadruped, and then there are a whole bunch of robotic stuff happening in various companies, whether it's G Research, I mean G Vernova, G Aerospace, a whole bunch of new startups that have come out in robotics. So in almost all of those cases, you have a very complicated state transition function. You have a somewhat simpler cost function, and you can use this algorithm to figure out what the optimal actions are going to look like. Yes.
So when you go, so after the last step, when you go to the second step, then you gotta compute x1. So
X1, yes. Because now you have U1, so you compute X1, then you compute P1, then you compute U2, and then you go back. Okay. So there are two things that I want to talk about now, having done the derivation for this algorithm. The first thing is I want to rederive, I mean, not rederive, but I'll give you some hint about proving the same result using the Lagrange multiplier theory, because we've already done it. Okay, so now we know Lagrange multiplier theory. Can I use Lagrange multiplier theory to rederive the same thing? So remember, we did derivation using some complicated, we had a whole bunch of equality constraint. We removed the equality constraint, we substituted xt with some functions of u, and then we did the derivation in order to get to this particular result. You can also arrive at this result by using Lagrange multiplier theory. So let's look at that example, or that theory. And the reason why that is cool, or that is important, is maybe you can use the method of multipliers or any of those algorithms to solve the same set of problems. So backpropagation is just one algorithm, and that viewpoint comes from this method. But the question then becomes, can you come up with a different algorithm which is not doing this backward propagation and forward propagation? Okay, so let's look at that. So I want to minimize j of u such that f1 or f0 of x0 u0 minus x1 equals to 0, f1 of x1 u1 minus x2 equals to 0, ft xt ut minus xt plus 1 equals to 0. So j is a differentiable function, right? J is a function. Well, I've written j as a function of u, but maybe I should write it as a function of both x and u. So ct plus 1 xt plus 1 summation t equals 0 to capital T ct xt ut. Now I am going to minimize over x and u. So I'm minimizing this function. I've called it j of u here, but I should probably call it j bar of x u. Now it's a function of both x and u. It's no longer just a function of u. And I have a whole bunch of constraints. How many constraints are there? There are t plus 1 constraints. I should mention that x naught is given. So I guess x naught is given. So you're not really optimizing over x naught. There are cases where you do optimize over x naught. So I'll give you an example for that. When you're sending a rocket to the moon, you need to figure out what's the location from which you want to send and what time, at what point of time do you want to send that rocket, because it's important. It will take different fuel depending on at what point of the time and at what location. you're sending that rocket to space. Naturally, there is also the constraint that you want it to be closer to ocean, because if in case you have to abort the mission, the thing falls in the ocean. So that's an additional constraint. But if you didn't have that constraint, let's say you were sending a rocket in space a million years ago, and so there's no humans on the planet, then x naught is also a variable. But in this case, we are not considering x naught to be a variable. X naught is given. Okay, so in order to apply Lagrange multiplier theorem, what's step one? When do we apply Lagrange multiplier theorem? When the constraints are regular. Okay, so how do I know if this set of constraints are regular? So it's a function of both x and u, and we have t plus 1 constraints. So in fact, if you do the computation, if you take the derivative with respect to, so I have t plus 1 constraints, right? So I have to take the derivative with respect to entire x and u. You will notice that actually you get a linearly independent set of vectors. Okay, so the constraint is regular. So one of the things, fact, and I think you can do it at home, the constraints are regular. So you take this is my h of xu equals to 0, and you take the derivative and I'll tell you why they turn out to be linearly independent. You see this, there is this block structure. This is a function of x naught and u naught, and then you have negative x1. So the derivative with respect to x1 would be identity, and then the derivative of this with respect to u naught is going to be independent of this identity matrix, because it's going to appear in different block in this huge x cross u matrix. So so that's why you will have like different blocks where you will have identity matrices, and different blocks where you will have gradient of x naught with respect derivative of f naught with respect to x naught and with respect to u naught. And because of those reasons, because different blocks will have different structure, you will realize that the entire matrix will be actually linearly independent, and therefore it's a regular I mean, all the constraints are regular. Now, the way I can do the Lagrange relaxation, the way I'm going to write the Lagrangian is Ct plus 1 plus summation Ct over all t equals 0 to capital T. So this is my cost function plus summation Pt plus 1 transpose Ft xt ut minus xt plus 1 t equals 0 to t. So this is my Lagrange multiplier. This is my lambda t plus 1. Okay, so this is my Lagrangian for this particular problem. So this is the cost function. This is f of x. This is lambda transpose h of x. Well, f of xu in this case. This is f of, well, f is already used, right? Okay. How should I write it? Anyways, I think you understand. This is the objective function. These are the constraints. This is the Lagrange multiplier. Okay. Okay, so what's the Lagrange multiplier theorem? Gradient of x of L equals to 0. Gradient of u of L equals to 0, right? Because I'm minimizing with respect to x and u. So at optimal solution, So because the constraints are regular, there exists a set of Lagrange multipliers such that the derivative of the Lagrangian with respect to the optimization variables at the optimal solution should be equal to 0. And this would give you the update equation for Pt plus 1. And this one will give you this particular result. Okay, I'll leave it as an exercise, but I think the important point that I'm trying to make here is you can actually come up with the same result that we have here using the Lagrangian method. And now remember, you have method of multipliers. That's one of the algorithms for solving problems of this type, right? You can actually apply the method of multipliers for this class of problems. So you don't have to apply the back propagation algorithm. Back propagation has a very specific requirement. You have to do forward propagation, you have to do backward propagation, and so on. If you're using method of multipliers, you initialize with any x naught, u naught, and p naught, and then you apply method of multipliers in order to compute the optimal solution in an iterative fashion. And I hope you will get the same solution in both the cases. I've not tried it myself. I've never seen it in any book, but technically you can use it. And I don't know what kind of solution you should be expecting if in case you happen to use this method of multipliers for solving this problem. The only problem that I see with method of multipliers is you could be in a situation where you're not satisfying these equality constraints. Technically, method of multipliers converges to an optimal solution if the system is convex. If the system is non-convex, then all bets are off. And then I don't know if these constraints would be satisfied or not. Hopefully, it should be satisfied. I think if the method of multiplier converges, I think we did one result in the class which said that eventually h of x star will be equal to 0, right? So hopefully, if the method of multiplier converges, you will converge to a point which is a feasible trajectory and is also optimizing the objective function. So just something to keep in mind, something to try. If your back propagation algorithm turns out to be too complex, you can apply the method of multipliers and hopefully get a solution quickly. Any questions on this? Yes.
So the way we defined the co-state vector,
Yeah.
Made it the Lagrange multiplier.
Well, yes. So the co-state vector that Pontryagin called it a co-state vector in 1948 turns out to be the Lagrange multiplier, even though this whole theory of Lagrange multiplier came a bit later. Okay, so that's why I'm saying that this is sort of a unified view of what happened at different points of time in history in completely different areas. Okay, so this is compression of 50 years of history of different groups working on different problems in different languages. So I think this paper was written in Russian. So therefore it's not even in the language that other people would understand, which is English in many cases. So okay. So in retrospect, everything looks connected, but if you're moving forward, everything looks disconnected because you come from completely different communities of research. Any other question? Okay. Wonderful. So those of you who work in Center for Automotive Research, this is going to be your bread and butter. Now, let me change gears a bit, and I'm going to try to solve the same problem, but instead of optimizing over action, I'm not going to optimize over policies. So now the question is, what exactly is a policy? So try to think about it. What exactly is a policy? What is university's policy? What does that document say? What exactly is it doing? So while I raise the board, I want you to think about it and give me a mathematical definition of what a policy is. What is a policy? Do you guys have any personal policy? Anybody wants to share what their personal policy is? So there are some policies that are sort of absolute, do not kill anyone or something like that, right? That's an absolute. But certainly in society, we have people killing each other. And so what's the policy in that case? There is a law, right? And the law book says if you are angry and you killed, here is the punishment. If you're not angry and you killed someone, here is the punishment, and so on and so forth. So policy is mapping a state to an action. Okay, so state is what happened, action is what the law is saying, that this is the punishment that the other person is going to get. So the policy, I'm going to denote it by, maybe I'll use pi t. Pi t maps the state xt to the action ut. So this is the state space. This is Rn and this is Rm. And this is policy at time t. It's also called a rule. It's called a decision rule. It's called a strategy. And so on. There are many names depending on which paper you are reading. I think in economics paper, they call it a decision rule. But then the modern economics paper and modern optimization papers are using policies. And some of the older papers are using strategy. Like 1980s paper would be using strategy or rule. Again, by the way, many of the stuff that we are doing, people also study in economics and business school, because even companies have to make policies in a dynamic setting. So people study this stuff in business school as well. So you get a mini MBA at the end of this course that nobody is going to recognize, but you still get an MBA. Okay, so we have a policy, and now I can write my performance index in terms of a policy. So now I'm going to write J as a function of pi, which is Ct plus 1, xt plus 1, plus summation t equals 0 to capital T, Ct, xt, pi t, xt. Remember, this is equals to ut. And then I have xt plus 1, ft, pi t, xt. And now my goal is to minimize j of pi with respect to all possible functions that maps x to u. Okay, so I have two different formulations here. One where I'm optimizing a function with respect to u. One where I'm optimizing the function with respect to the policy pi. Why should one formulation be preferred over another? So what's the benefit of having things written in terms of a policy pi? What is the benefit? So instead of figuring out what the optimal action is, now we are looking at the state. We are not figuring out what the optimal action is. We are looking at the state. We have the optimal policy in some sort of book, codified in some sort of book. It could be constitution of a country. It could be some university policy handbook. I'm sure all of you are aware of the grad policy handbook or undergrad policy handbook. So there is a handbook, and I'm going to go look up the handbook, and I say, okay, at this particular state, this is what my action should be. And I'm going to apply that action, and I'm going to accrue that cost. Okay? So why is policy better than this action? No, action is less expensive, right? Here you are optimizing over Rm cross T. Here you are optimizing over all functions from Rn to Rm. So this is way more complex than that. Yes.
It's more possible to comprehend the possible like structure.
Good point. So here I'm going to tell you, you have an aircraft, you go like this, you go like this, and then you go like this, and you're done. Here I'm saying you have an aircraft, I'm going to give you a book at the beginning of the aircraft, and every time something happens, you read the book and then you start driving the aircraft. Why is this better than just saying you go like this, you go like this, and you go like this? Yeah.
Maybe it's like easier to always understand when we put a constraint on the policy, how that would, cause if you constrain your policy, it's easier to understand how your states would
evolve. Yeah, okay. So you can potentially constrain the policies for sure. We'll do that constraining of policies in a bit, but not today. So right now it's all unconstrained. So we are not constraining the policies by any means. Any other reason? What happens when you are flying an aircraft, or when you are making a robot go around, I don't know, outside OSU? Like you see a lot of these robots moving around OSU. What happens, generally speaking, when you are left this robot in the wild to do some activity? Yeah.
You might do something that you don't want it to do.
Yeah, you don't want it to do something, but what is it that you don't want it to do? Yeah.
In this scenario, you're only doing an action, so you're training it on the data that it already knows. Whereas the policy, you take in new data and make a decision.
Wonderful. Okay, so policy can look at a new data and make a decision. I think I want to zero in on that particular argument. So why exactly new data appears in real world scenario? Why would there be new data in life? Yeah. Sorry?
For example, why all of a sudden the weather changes.
The weather changes. What else?
That's what I was saying. A lot of uncertainties.
Lot of uncertainties that gets realized. So if a robot is moving around outside, what's the uncertainty that gets realized? I don't know. Somebody just keeps walking around. Somebody's crossing the road. All that stuff is uncertainty for that robot. Yeah.
Yeah, you can't test every scenario.
You can't test. Wonderful. Yeah, you cannot test every scenario. You're sending a rocket to space, and there could be crosswinds. There could be bird strikes. There could be a lot of other things that can happen. So what this philosophy tells you, you know the initial state x naught, I can tell you exactly what actions to pick, as long as there is no uncertainty in the system. So you know ft exactly, you know ct exactly, and real world is full of uncertainties. Okay, so in real world there is noise, there is weather, there is people walking on the road, there is uneven terrain. If you have a robot that's going up and down the mountains, or I don't know, driving in a field, there could be deer in the fields, and the robot is supposed to figure out, okay, now there is a deer, what am I supposed to do, right? So initially in 1949, people said, okay, if I know the initial state, if I'm sitting here in the field and I'm to get the corn, I'm supposed to get all the corns in the field, I'm going to go up and down and take all the corns. No matter if there is a deer, I'm going to take in the deer as well. If there is a rabbit, I'm going to take in the rabbit as well. That's not acceptable. Okay, we need to create systems where if there is a deer, we just stop, wait for the deer to pass, and then we start harvesting. So the policy allows you to do that. So even though you have a deterministic system, you have a cost function that you know very well in advance, you still want to compute the policies, because in case something happens, I will know exactly what to do, because the rule book is going to tell me what exactly to do, what's the optimal action moving forward. Okay. Typically, when you have very strong noises, then you are in the realm of what is known as stochastic optimization. We are not covering that in the class, but I am teaching another class on Markov decision processes this semester, which I think nobody else is taking in this class. So you probably wouldn't know about it. So if you have strong noises, you do stochastic optimization. If you have very little noises, you don't do stochastic optimization. You do deterministic optimization. So you keep your system model as deterministic, but you compute policies so that if in case something bad happens or something wrong happens or some small perturbation happens, you can adjust your situation to the new state of the system. Okay, so if when an aircraft is flying at 900 whatever, say 500 miles an hour, and if there is a crosswind of 10 miles an hour, it's just a noise on the system. But if there is a crosswind of 100 miles an hour, that's a problem. Okay, so we don't consider the situation where there is 100 miles per hour crosswind, but we do consider the situation where there is 10 miles per hour crosswind. Okay, so wonderful. So what I mean to say is this is not robust to noise. This is robust to noise. Okay. So if you don't have noise in the system, you can use this sort of Pontryagin minimum principle based optimization approach. If you have a lot of noise in the system, you better use the new approach where you are optimizing the policy. So this work was done in 1949 by Isaac and 1952 by Bellman. Both of them in US. So this one was in USSR. They wanted to send rockets to space. This was in US. What were US trying to do? Send rockets to space. Okay, it's the same mission. But they came up with two completely different theories. One theory which said, okay, I'll do deterministic optimization using backpropagation. The second one said, let's try to optimize over policies because policies could be robust to noise. If you're sending rockets to space, you want your system to be robust to small perturbations in the state. Wonderful. So I want to talk about Bellman's principle for optimality. Yeah, I have 10 minutes. Bellman's principle of optimality. In order to introduce this Bellman's principle for optimality, let me define J of t pi t to capital T equals to C t plus 1 xt plus 1 plus summation k equals t to capital T ct ck xk uk. This is known as a truncated cost. Cost to go. So cost to go is the typical term. We refer to this particular remaining cost of the system. So at every point of time, I'm looking at the cost moving forward. So I'm standing at time t, my state is xt. I have this whole bunch of costs that I have to spend all the way until the end of the horizon, and then this is the cost that I have to pay at the terminal time step. So Bellman said, we need to solve this problem. Okay, so I'm going to get a pi star, which is the optimal solution to this problem. But pi star is a very big set of functions, right? You have pi 0, pi 1, pi 2, all the way up to pi t star. So he said, we need to simplify the problem a bit, because at every point of time, I can't be computing capital T number of functions or capital T plus 1 number of functions. Remember, when we were talking about all this rocket example where rocket is moving into the space, capital T could be of the order of 1 million. or of the order of 100,000. So you can't really come up with 100,000 functions like this directly by optimizing this objective function. So he wanted to figure out how to simplify this whole process. And he came up with this Bellman's principle of optimality, which says that pi 0 star to pi t star is optimal for j if and only if pi t star to pi capital T star is optimal for jt for all t between 0 to capital T. So this is the tail of pi star. This is cost to go at time t. So the tail of the policy is optimal for the cost to go at time t, for every t. Okay, so what does this imply? This implies that pi t star is optimal for jt. It implies that pi t minus 1 star is optimal for jt minus 1, sorry, j pi t minus 1 star pi t star is optimal for jt minus 1, and so on and so forth. Now this looks interesting. So I wanted to solve this big problem with capital T horizon length, and Bellman came and said that, look, you can do it sequentially. You don't have to do it all at once. What you can do is compute the optimal policy for the final cost to go, then compute the second to last optimal policy for the cost to go at time t minus 1, and so on and so forth. Once you have computed pi t star, you don't have to compute it here. You only have to compute this one. Once you have computed this and this, then you only have to compute pi t minus 2 star, and so on and so forth. So this allowed you to get what is known as a dynamic programming decomposition of the original problem. So this is the original problem. I want to minimize j of pi. Very complicated. Bellman came to our rescue back in 1952. He said, don't worry about it. Just do the final time step optimization first, and then keep going one step back. That allows us to get what is known as dynamic programming recursion, and we are kind of sort of out of time. But let me write down the recursion for time capital T, and then we'll figure out what to do in the next class. So I'm looking at j of capital T of pi t. This is ct plus 1 xt plus 1 plus ct xt ut. Ut should be replaced with pi t xt. This is, by the way, maybe I should write it as j capital T of x capital T pi capital T. I can replace this with ct plus 1 ft xt phi t xt. Okay, so I have the action ut to pick. This is my ut. I have sum of two cost functions, and I'm trying to minimize the cost, right? So this is my minimization problem. There are people who maximize the reward, but we are not looking at the maximization. This class is all about minimization. So we'll minimize the cost function. So the way to minimize it is I'm going to call this function v capital T of xt. This is minimum of u capital T ct xt ut plus ct plus 1 ft xt ut, and I'm going to define phi t star of xt as the argument of ut. So I set up this optimization problem. For every xt, I'm setting up an optimization problem. I have minimization of this cost function with respect to ut. I'll apply gradient descent and stuff to figure out what my ut star is going to look like. I'll store that as the policy phi t at xt, and the value that I get, which is the evaluation of this cost at ut star, I'll store that in the value function vt of xt. Okay, so this is going to look like a function. Okay, so think of it, for the time being, think of it as a matrix. So you will have a whole bunch of xt, and you are going to write what the value at that particular xt looks like. This is going to look like a lookup table, or it's going to look like a book, where for every xt, for every state, it will tell you what exactly is the optimal action ut star. How many states are there in Rn? How many xt's are there in Rn?
Is it n?
No. It's infinite, right? Because it's a continuous variable. So you have infinite number of states in Rn, infinite number of vectors in Rn. You have to compute this value at infinite number of vectors, and you have to compute this policy at infinite number of vectors. So your rule book is going to contain infinite number of vectors and what you are supposed to do at each of those potential vectors. So if your state is 0, 0, 0, this is what your action should be. If your state is 0.1, 0, 0.1, this is what your action should be, and so on and so forth. So the rule book is going to look very complicated. So for now, we'll forget about this complications of the rule book. We'll deal with it when the time comes. But for now, let's assume that you could create this rule book, which is infinitely long, and you can store the value function in this particular fashion, and you can store the policy by solving this argument. And in the next class, we'll talk about how to use this value function and the policy to compute pi t minus 1 star, pi t minus 2 star, and so on. And that will give us the dynamic programming algorithm. Okay, so thank you so much, and I'll see you on Wednesday.